So we're going on to the next section called Riemann sums. They're named after a mathematician. We'll talk about that later. And we are starting to tie in, we're still doing anti-differentiation. This whole unit 5 is about the antiderivative, also known as integration. And so we're just going to be seeing more tie-ins with what exactly that means as we move along. So today's lesson is not going to seem exactly like integration or anti-differentiation in the beginning, but we'll get there. So let's talk about this scenario that we have. You're traveling on the New York State Thruway from 3 to 5 o'clock at night at a steady rate of 75 miles per hour. You put the cruise control on, 75 miles an hour exactly the entire time. How far have you traveled? Well, you guys at this point will have no problem realizing that if you are traveling for 2 hours at 75 miles per hour, that you went 150 miles. So what is the relationship between rate, time, and distance traveled? So we saw this before when we were doing some of our optimization problems, that the distance traveled is our rate times our time. You guys did that intuitively. How far did we go? What's our distance? Well, at 75 miles per hour, that rate, for the 2 hours, you did 75 times 2 and got 150. So now we want to graph this scenario. We want to graph our traveling for 2 hours at 75 miles per hour. So we're going to be graphing 75 miles per hour. We're graphing the rate that we're traveling, or in other words, the derivative. So what will our units on the independent variable be? Well, if we're going to be graphing miles per hour, then we're going to be talking about our hours. So our time in hours on the horizontal axis. So time in hours. And then our dependent variable is how fast we're going. So that's going to be our velocity axis in miles per hour. Remember, a derivative is a rate. All right, so let's make it make sense. Let's start our time at time noon, because then we can talk about 1 hour, 2 hours, 3 hours, 4 hours, 5 hours. So that's 3 o'clock, 5 o'clock. And then our rate of 75 miles per hour being constant, we're going at a constant rate. This is our velocity of 75 miles per hour. So this will be miles per hour on the dependent axis. All right, so we're going to look at this scenario graphically, and I have 2 typos here. Sorry, we're not on a train. I was going to do a train problem, but we did a car problem. So what do you notice about the distance traveled by car and the area of the rectangle whose base is the time interval from 3 to 5? So I'm asking you to make a rectangle. We don't know why yet, but that's okay. And I ask you, what is the area of this rectangle that we formed? Well, its width is the 2 hours. Its length or height is the 75 miles per hour. And then it turns out the area is 150. So it's 2 times the 75, which is 150 miles. So what did we really do there? We actually did the rate times the time. 2 hours at 75 miles per hour gave us that distance. This doesn't seem as important as it really is, which we'll see over the next couple of lessons. So the importance of this concept cannot be understated. The area under a rate curve, will always give us the value of the position units. Meaning, we did a miles per hour graph, and the area under this curve gave us miles. If this curve had been, instead of miles per hour, had been in gallons per minute, then the area under this curve would have given us the number of gallons. If the curve, instead of being miles per hour or gallons per minute, had given us dollars per week, then the area under that curve would have been in dollars. Or if we had milligrams per hour, maybe you're a nurse and you've just given a medication and you want to know when you can give it again, how many milligrams have been disposed of by the body over a certain number of hours will be what we're looking for. So this is super important. If we have a rate curve, if we have a derivative graph, then the area under that curve will always be what we call the position units, or the units of the original function whose derivative we have taken. All right, so let's do another example. So let's suppose we've got a car moving. I'm going to tell you it's got increasing velocity, so it's going faster and faster. And say we've looked down at the speedometer and measured that velocity every 2 seconds. And then we recorded it in a table as shown in the chart. So we want to know how many feet has the car traveled during 10 seconds. Now notice our velocity is in feet per second. So our independent axis is in seconds. Our velocity axis is in feet per second. So as we just saw, how many feet have we traveled will be the area under the curve, or the area under what we graph when we graph this data. So I want to start by doing that. Let's graph what we have in our numerical chart here. We have 2 seconds, 4, 6, 8, and 10. And we're graphing a velocity, let's see, 10, 20, 30, 40, 50. So at 0 seconds, we're at 20. At 2 seconds, we're at 30. At 4 seconds, we're not quite to 38. At 6 seconds, we're at 44. At 8 seconds, we're at 48. And at 10 seconds, we're at the 50. So a little something, something like that. All right, so we want to find the area under this curve because, as we've just discussed, if we find the area under this curve right here, that will let us know how many feet we have traveled. Now, what we're learning here is something called the rectangle approximation method. We approximated, and actually in this case got the exact answer by finding the rectangle's area under this curve. Lucky for us, in our first example, the top of this curve is just a nice straight horizontal line, so we have a perfect rectangle. Down here, we are not going to have a perfect rectangle, but we are going to get an approximate answer for how many feet we've traveled by calculating a rectangle under this curve. Now, we can do this 2 ways. Let's talk about making this whole entire curve one big rectangle. Let me move this up a little bit. Well, if we make it one big rectangle, then we have a 10-second base. That's our width or our length, whatever you want to call it. And let's go over here. But to make this a rectangle now, rectangles are, they're like this, straight across the top and on the sides. So I am going to top this off in order to make a rectangle. Now, we can clearly see, if we find the area of this rectangle, that we are grossly overestimating the amount of feet, because all of this space up here in purple is more than the area under this curve. But let's just do it anyway. So we have a length of 10 and a height of, this curve goes up to 50. So 10 times 50, we're saying that this car went 500 feet. Clearly, it did not go 500 feet. That's a gross overestimate. So we can certainly say, well, it's gone no more than 500 feet. At the most it's traveled, and we know it's less than, but it's definitely no more than 500 feet. All right, let's try this problem again. Let me use pink this time. But instead of making my rectangle as high as 50, let's make my rectangle, let's use the other side here. Let's say my base is 10, but this time let's use that 20. And let's call that our rectangle. That's a clear underestimate of how many feet we've traveled, but it's a rectangle, taking up the 10 seconds of time. So if it has a base of 10 and a height this time of 20, then we can say that maybe we've gone 200 feet over those 10 seconds. Clearly, 200 feet is an underestimate. So what might we do in order to come up with a better estimate of how many feet we've actually gone? Well, maybe some of you will be thinking, well, 500 is definitely too much. 200 is too little. Let me average those two values. And that's a brilliant idea if you thought of it. So didn't go 500 feet, but didn't go more than 500. Definitely didn't go less than 200. So the average of those two is 700 halves, or 350 feet. We don't know if we've actually gone 350 feet, but 350 feet is a much better estimate for how many feet we've gone than the over or under of 500 or 200. So what we've done here is we've looked at three very specific types of rectangle, R for rectangle, A for approximation, M for methods. The rectangle approximation method. The first one we did here is called an LRAM, L standing for left. When we did this first rectangle, we used the time interval of 10 seconds as our width, but our height was on the left-hand side of this whole area. So that was a left-handed, left rectangle approximation method. When I did the pink one, I got my height from the right-hand side. Oh, I did that backwards, didn't I? Does she know her left and her rights? Sorry, that's a right. That's a left. So we have a right rectangle approximation method from using the right-hand side, a left from using the left-hand side, and this last one is going to be called an ARAM because we found the average of the two